Uh, Good afternoon. So far, we have seen various kinds of distributions, distribution functions of jointly distributed random variables. We have also seen what are conditional distributions, but sometimes random variables being random variables that they can take any value over a certain range and according to their distribution functions. It becomes very useful to have certain single numbers which will indicate that what is known as number one, what will known as that this, while they are random, what is the kind of an average property of this random variable. On an average it takes what value, or that is sometimes called measure of central tendency. That is, if you take all numbers, then on an average what kind of values that number takes. Number one. Number two is that is not enough, because for example pictorially it becomes interesting to see that suppose you have a random variable. So it can take, suppose these are number of samples. So the random variables take values say in this region. So if you take their average, then you can say that it is, let us say, around the point AB. This is B, this is A. So this, all these dots are random, but you can say that they are on an average spread out around the point A and B. This is useful to know. Secondly, it is also useful to know that suppose you have these black dots which are spread out around the point AB, and you also have these red dots which are spread out still around A and B, but much more widespread around the point A and B. So it's not just enough to know whether they are spread out from the point A and B, but it is also important to know that is in general how much they are spread out from the point A and B. So this is sometimes called, so we need to know this, that this point A and B, and what we say, we need to know what is known as a measure of dispersion. So how much they are dispersed around the point A and B. This we have seen in our school statistics also. So in general we need to, these two quantities become very important numbers to characterize, let us say, a single random variable, and we are going to talk about these two things today. They are called the mean and the variance. So lecture 5 is about a mean and a variance. So firstly, the mean is also sometimes called an expected value. Now what do we mean by this expected value? I mean, a random variable is random. If you make an experiment today, you will get one value. If you make an experiment tomorrow, you will get another value. So what do we mean by an expected value? So what we mean by an expected value is actually in the sense of average. What sort of average? Suppose we do a large number of experiments. Suppose we do n experiments. Okay. Let us consider a random variable x, a random variable x which can take values either A or B or C. So suppose we do n experiments, that is, we pick x n times, and of them n A times we get A, n B times we get B, and n C times we get C. Obviously n A plus n B plus n C is equal to n. Now, if we say that, what do we mean by an expected value of x? What we mean is that if we just added up these values as we picked up over these n experiments and then simply made an average, what would be the value? So, obviously, the value would be a into n a plus b into n b plus c into n c by n. This is our expected value. So, what we get is a into n a by n and plus b into n b by n and plus c into n c by n. Now, if we take this, if we take the limit that n tends to infinity, then what do we get? We get a into probability of getting an a, that probability that x is equal to a, plus b into probability that x is equal to b, plus c into probability that x equal to c. So the average is sigma. You can say that over all I, xi. Now we are saying that x takes values over an index set I. For example, x1 is a, x2 is b, and x3 is c. So x and then probability multiplied by probability that x is equal to xi. If you sum this, then we get what is known as an expected value. So for a discrete random variable, which is easier to understand, by what we mean by an expected value of x is that it is simply xi into probability of x is equal to xi. In other words, we every time we pick up the random variable, we perform the experiment, we actually note it down, suppose in a copy, and at the end of a large number of experiments, we simply sum whatever we have copied in our book and then divide by the number of experiments. That is my expected value, correct? Now, what happens when we have a continuous random variable? Obviously, in a continuous random variable, the number of values that x can take, namely the xi's, is infinite. So the index set is actually infinite. So we have to actually this summation. Now we have to perform over very small intervals, and then this summation will finally become an integral. Okay. So we write, now we try to write this exactly like the random variable. We want to write this summation for also a continuous variable, and we write that if we take very small intervals, so limit of delta x tending to 0, and so obviously if we take very small intervals, then the number of intervals will become infinity. So when we are calculating the probability over the real line, naturally we are going to have an infinite number of such intervals. So k indicates that interval index. So we have k is equal to minus infinity to plus infinity. This k delta x now becomes the value, now becomes is equal to xi. So in the kth interval, what is the value of x? It is k delta x. So what is the probability? So when we take this, so this takes the value of xi, and now we want to calculate the probability that it falls between k delta x and k plus 1 delta x. What is this probability? That probability is nothing but f of k delta x, where f is the probability density function, into delta x. So now this k delta x, f of k delta x, delta x. This sum, if we do from k is equal to minus infinity to plus infinity, and if we now taking delta x in the limit, if we replace k delta x by the value x, this k delta x by the value x, and this delta x by the differential dx, then we will get the, and then as we take delta x tends to 0, this sum will become the limit. So we will get the definition of the expected value of a continuous random variable, which is nothing but minus infinity to plus infinity x fx dx, where fx is the probability density function. Okay. So, this is a very important quantity and often of great interest in various kinds of analysis. So, this is called the expected value of a random variable capital X and is denoted as E of capital X. Now, let us see. So, this is the expected value of a random variable. Now, suppose we have a function of a random variable, or in other words, suppose we have a random variable y which is a function of a random variable x. We have already seen that if we have a random variable x and if we have y as another random variable which is constructed by taking a function of x, then we have already seen how to calculate the distribution functions, density functions of y. So, we want to so now again if you want to find out expectation of y, then it will be nothing but minus infinity to plus infinity y. Now, this is the density function of y dy. This is the old expected value definition applied to y. Now, we want to write it in terms of x, because actually in many cases actually y is a derived quantity. The original random variable is x. So, in all probability we will know the density or the distribution function, that is whatever probabilistic description we will have, we will in general have it for x, right. So, we have to now express the expected value of y in terms of the probabilistic description of x and the function g, right. So, it turns out that the thing that this is nothing but minus infinity to plus infinity gx, this y becomes gx. Now, we want to express this integral in terms of x, because x is the original random variable. And what is fyy dy, that is what is the probability that y becomes, I mean y stays between y and y plus dy, that is the same since we are considering all possible values of y. So, obviously, we are also covering all possible values of x. So, all you need to do is that you take an interval of x and you just find out the corresponding value of y. So, in this way rather than varying y, you vary x. For each value of x you consider gx and then cover the integral. So, it is the same thing, right. Only thing is that that's the same thing. Note that we have not exactly replaced this integral by this one, right, because if you want to do fy by y dy, then as we have seen before that you have to actually find out that what are the values of x that gives you the same value of y gx, and then you have to take intervals around those x's, that is if y is equal to gx has a root xi, then you have to consider intervals around those xi's, and you have to take intervals of length dy by g dash xi, all that. But then finally, it will turn out that if you are taking a variation of all possible y's, then that is equivalent to taking the variation of all possible x's, right. So, these are rather somewhat mathematical arguments which actually show that this integral and this integral are equivalent. Now, it turns out, I mean having noted that, it turns out that now this is, you can sometimes say that this is an expectation operator. So, you take a random variable x and if you operate it by the expectation operator, you get a constant which is called expectation of x, right. So, its value like a function. Now, the first thing we are trying to note is that this operator is actually linear. What do we mean by linear? What we mean by linear is that if we take expectation of a sum of quantities, then that is equal to the sum of the expectation of these quantities. So, the expectation operator is actually, so expectation of sum is equal to sum of expectation, right. So, in that sense it is linear. I mean just like for any linear operator L, a1 x1 plus a2 x2 can be written as, this is the basic superposition theorem idea, is a1 into L of x1 plus a2 into L of x2. So this is a superposition theorem which any linear operator satisfies. So in a similar sense, this operator is called linear. Now let us consider more complex functions. Suppose z is a function of both x and y, that is x, y and z are actually, x and y are a collection of jointly distributed variables and z is a function of x and y, right. So now what is the expectation of z? So previously we had a function in one dimension, y is equal to gx. Now we are considering a function in two dimensions. So z is equal to g of x and y both. We will do exactly the same in the sense that previously we had taken the integral over the x axis. Now we have to take an integral over a region, because now we have a two dimensional space over which z takes values. So the basic defining integral is the same, minus infinity to infinity z fz z dz. That is the basic definition of an expectation operator. Now if we take this fz z dz, then that is what is the probability that z is between z and z plus dz. So now we have to exactly compute the region of x and y for which z takes the value of z plus dz, between z and z plus dz. And now so we have to find out that what is the probability that under the given random variable descriptions, that is under the joint probability distribution function of x and y, what is the probability that x and y take values in that region dz for which z takes values between z and z plus dz. So now we have to basically do an area integral. So exactly that is what we are doing. So we have a double integral because there are two axes, and we have a joint density function fxy of x and y dx dy, and we are computing it over the region dz for which z takes the value between z and z plus dz. And now it turns out that that is nothing but, again by similar arguments, that is nothing but minus infinity to infinity gxy fxy dx dy, right. So again, since z we are varying between all possible values minus infinity to plus infinity, so that is equivalent to sweeping x and y over the whole region minus infinity to plus infinity, and then for each x and y pair, that is for each x and y square, simply pick up the value of z which it takes while it takes in that square, and then sum the integral. It is one and the same thing. So this is how you evaluate the expectation operator, which is the expectation of a quantity z which is a function of two random variables which are jointly distributed. Now let us come to what is known as conditional expectation. This is that obviously the expectation of a random variable becomes totally different if some facts are given. For example, one of the simplest examples is that what is the expectation that a family has both sons, that a couple, among all the couples having two children, what is the probability that a couple has two sons? Okay, it is obviously 1/4, assuming that the probability of the probability of having a daughter or a son is actually half. Okay, so the probability of having both sons is actually 1/4. But what is the probability of a couple having two sons, already given that it has one son? Now it is half. So you see that the probability of a couple having two sons changes whether you give the information that it already has a son or you don't give the information, right. Why does it change? Because now when you will be looking for couples having two sons, you will obvious, since you are already given that the couple already has one son, so you will be looking among couples who already have one sons rather than all the possible couples, right. So you see that this is called conditional expectation. So the expectation, this is the expectation of a random variable when certain facts are already given, certain facts are known, they are not random, right. So if certain facts are already given, what is the expectation? Obviously that is going to be different. So now we are going to talk about that. So exactly in a similar fashion, that what is the expectation of x given an event m, given some relationship, some information about x through the event m. So obviously it is going to be the conditional density function now. Previously it was the ordinary density function, but now it is going to be x conditional density function of x dx, because this actually indicates the likelihood of x occurring given the information m, right. So for a case of discrete random variable, it is going to be xi, probability that x equal to xi given m. So always we are going to consider that fact m, which is the condition given, right. Let us take an example, that suppose x is uniform. Suppose we are talking about the persons, we are just assuming that people must be aged between 0 and 100. This, we are actually ignoring the people who are more than 100 years old. Actually anyway their number is very small. So if we assume that the probability distribution function of persons is uniform, that is there are equal number of persons between the age 0 and 1, 1 and 2, 2 and 3 and so on, right. So then if somebody asks that what is the probability that a person's age is greater than 65, what is the probability? So you have what is the probability density function? The probability density function is like this, that is 1 by 100, the interval of age is 0 to 100, total probability must be 1 and this has to be uniform. So therefore this is 1 by 100. So this is the probability density function. So what is the probability that if you pick a random person from the street, what is the probability that his age is going to be greater than 65? So obviously it is going to be this one. So it is going to be 0.35, correct. 100 minus 65 into 1 by 100. Now what is the conditional density function? What is the conditional density function given the fact that let us say x is greater than 65, that is okay. So in that case obviously since it is given that x is greater than 65, so therefore x, so f of x when x is less than 65 is 0, because when it is given that the x is greater than 65, therefore there cannot be any person, we cannot choose any person whose age is less than 65, so we will get 0 here. So all the people will get are now from this region. So obviously now the probability density function is going to be this divided by 0.35, because now over this region only this conditional density function is going to be 1. So the conditional density function is going to be fxx by 0.35, right. So now if somebody asks me that if you pick a large number of persons from persons who are aged greater than 65, what is the average age that you are going to find? So that is going to be the expected value of x when x is greater than 65 already given. So it is the conditional expectation of x given x greater than 65, and then if we just put this conditional density function, then what we will get is nothing but 82.5, which is nothing but the midpoint between 65 and 100. So since the probability, this is also obvious, I mean since the probability density function is uniform, so obviously the mean is at the middle. So if you are considering people between 65 and 100, it is obvious that the mean is going to be at the middle of 65 and 100, which is nothing but 82.5, right. So this is called conditional expectation. Now we want to show that a particular, an interesting, what is a conditional distribution? That is, we want to compute conditional distribution mathematically, right? So previously we had talked of, we have just now found conditional distribution of a single random variable. Now we are going to find out the conditional distribution of a random variable y, which is jointly distributed with x through the distribution function fxy. Okay, so obviously, what is going to be it? What is expected? What is expectation of y? We are now talking about only continuous random variables. So now, what is expectation of y? Again, what are you going to do? You are going to make enough experiments, and then from each experiment you are going to take a value of y, and then simply sum them up. So how do you and in doing this you have to consider the whole range of x and y, right? So you are given the joint density function. So what is the probability that a y, if you perform an experiment, you will get y? So that will be obviously fxy xy dx dy. That is, so this is the probability that you will get a value y here. Now here x is a free variable, right? So now you first integrate it for all possible x, and then you integrate it for all possible y, then you will get the expectation of y. So now let us try to rearrange the integral. So we are writing at minus infinity to plus infinity, minus infinity to plus infinity. What is fxy? What is this? That is, if we write it, what is fxy xy? That is, what is the probability that x falls between x and x plus dx, and y falls between y and y plus dy? That is nothing but fxy dx dy. So we can also write it as, what is the probability that y is, this is nothing but Bayes rule. Okay. So we are now writing the joint occurrence of x and y as y given x, that is the probability of y given x, and then the probability of x. So we can always write it. So in doing so, we have expressed the total probability as a conditional probability of y given x multiplied by the probability of x. Okay. So now we can, one of these integrals is actually over x, the other integral is over y. So now we are saying that we take one integral inside and we sort of bracketed these terms, So now this is expectation y fy given x dy. So as if this is the conditional expectation of y, this is nothing but the conditional expectation of y given capital X is equal to small x. So you are saying that first you find out what is the expectation of y if given, let us say, x is equal to 1. Then you find out what is the expectation of y if given x equal to 2. Then you find out what is the expectation of y given x equal to 3, and so on. So each time find out the conditional expectation of y conditioned on a given value of x. Then weight each of these by the probability of x, which is the same thing. So that is what we are doing. So first we are calculating the conditional expectation, and then we are weighting it, because we have to multiply it by the probability of x. So the probability of x is fxx dx. So then we are weighting it using fxx dx, right? So what you actually get is this one. So you get expectation of y given capital X is equal to x, which is this integral, multiplied by fxx into dx. Now this looks like what? This looks like simply like previously, just like minus infinity to infinity. Remember gx fx dx, if y was is equal to, so gx fx dx, if remember that if y is equal to gx, we derived, so then expectation of y is equal to minus infinity plus infinity gx fx dx. So now what is this gx? This gx itself is becoming expectation of y given x equal to x. So what is this g function? This g function is nothing but the expectation operator. So now we are what are we calculating? We are actually calculating expectation of gx, because we are calculating expectation of y. Now y is equal to gx. So we are calculating nothing but expectation of gx, but gx happens to be this. So we are actually calculating expectation of y given x. So what this is very interesting, and it's sometimes so useful, that if you want to calculate the unconditional mean of y, it becomes sometimes very useful to first calculate a conditional mean as a function of x and then take an expectation over x. So remember that this expectation is over x, while this expectation is over y conditionally with x. So in other words, what I wanted to say is that this expectation operator, at least the conditional expectation itself, is like a function of x. So when you write expectation of y given x, it is a function of a random variable x, simply because the expectation value depends on x. So if you take x greater than 65, you will get one value. If you take x greater than 55, you will get another value. So obviously this expectation of y given x greater than 65 is going to be different from expectation of y given x greater than 55. So in that sense, it is a function of x. So the conditional expectation itself is actually a random variable which is a function of x, right? So this is interesting. Next, we can actually again we can extend this same thing for functions of two random variables. For example, if you have z is equal to gxy, so you have two random variables x and y, and z is a function of a random variable. Now what is expectation of z? So obviously expectation of z is expectation of z given xy. Same thing, same rule we are applying, only thing is that this expectation is now over x and y both. So this expectation is now over x and y. So exactly, you see what, that is precisely what I am doing. This is my conditional expectation, that is this term is this term, and then I am taking joint expectation over x and y. So I have added the joint distribution, I am multiplying by dx dy, and I am integrating over minus infinity plus infinity. So we can also write it like this. Similarly, I am just showing different forms. Suppose it is not always necessary that it has to be conditioned both on x and y, it can be conditioned on one. So for example, suppose we have expectation of z given capital X is equal to x, y is a free variable. So then what do we do? So now we have to do expectation of z given x and y, or rather conditional expectation of z over x and y given x is equal to x. So now x is fixed, we cannot evaluate this integral over x. So this outer expectation now must be made over only y, because x is fixed. So when we write it as an integral, we have to write it over y. Okay. Remember that this x is taking value. So this x actually freezes this x, while this y is actually a free variable of integration which is integrated here, and this is the conditional expectation, and this is actually a function of, this is actually some function of g dashed of x and y. So we will get it as a function of x and y, but for x we have to put the value small x. Now it will become a function of y, it will become a function of small y. So now you have to do g dashed of xy, fxy of xy, and then dy. So you have to vary y over the integral, you have to keep x held at small x because you are given this, and you have to evaluate this integral. So in this way you have to evaluate conditional means conditioned over various kinds of facts which may be stated in terms of x and y. Okay. So, basically the idea was to show that how to compute the expected value of a random variable under various conditions. So, we have seen firstly how to calculate ordinary expected value, then we have seen how we can calculate expected value if it is a function of a random variable. We have seen how to calculate when it is a function of two random variables. We have calculated how to calculate if some constraining facts are given as conditions. So, we have seen how to calculate conditional expectations, again normal conditional expectation, then conditional expectations of function of one variable and function of two variables. Okay. So, these are roughly speaking, these are the various ways which cover. You can obviously generalize it for n variables, etc. But this covers the basic crux of computing of expectation. Now we talk about, we gradually come to the concept of how much. So, now we have an expected value, something like a center of this distribution. Now we want to somehow characterize that how big is this ball around which the value usually, the random variable usually takes value. What is the, of course the ball is, strictly speaking it can take any value, but on an average, that is, can we say that, let us say with probability, what is the expected value of the dispersion? Okay. So, we try to express that, and for doing that we first introduce what is known as a moment. So, what is a moment? So, a moment is an expected value of a certain special quantity. So, what is that? So, now in place of gx we are choosing a special function. So, this is like gx, only thing is that we are choosing a special form of gx. So, what is that form? So, the rth moment of x about a is defined as when you put this gx and you take the expected value of that gx, then it is called, so it is nothing but an expected value of x minus a, this random variable, whole to the power r. Now, typically we can, where do we choose x? Where do we choose a? So, obviously what are we trying to find out here? We are trying to find out some measure of how this random variable is, how much it is away from a, small a. So, this small a number we can choose as anything, and in general we are very much interested to know that what is the expected value by which a random variable is away from its expected value. So, it has an expected value somewhere and it takes values around it. So, for every value it has some x minus a, this is my a, which is equal to expectation of x. For every value that x takes, there is a dispersion, there is a distance. So, we are just trying to find out that what is the expected value of these distances. Okay. So, that somehow indicates that on an average, how much are the random variables, how much away from them. So, if this expected value is large, it means that the ball is large around the mean. Okay. So, typical, so obviously we very often, this is a very common choice that we choose a is equal to expectation of x, and since Euclidean norms and square norms are so popular and makes so much sense to us in the physical sense of the word. So, we often take a second moment about mean. So, this is a very common choice, taking the second moment about the mean. So, what we compute is x minus, now because mean, so a is expectation of x and r is 2. So, this is called the variance. Okay. And a bit of algebra will tell you that it is nothing but expectation of x square minus expectation of x whole square. So, that is very standard algebra, and we also very commonly define another term called standard deviation, which is nothing but the variance, the square root of variance, or rather standard deviation square, or sometimes we very commonly denote it as sigma square is variance. Okay. this is about a single variable. In a similar way, suppose we have two variables, then whenever we have two variables, then we have to not only say, when we have one variable, we have to just describe that how much it is away, if here is the expected value, how much it is away from the expected value. Now you have two variables. So you are going to have, so suppose you have two variables x and y. So now x is going to be away from its expected value, expectation of x, and y is going to be away from its expected value, expectation of y, and this is going to happen together. So now you not only want to find out how much, by how much x is away from expectation of x and y is away from expectation of y, but you rather want to find out that whether these things happen together, or is it that when y is close, x is far away, and x is close, y is far away. So you want to also characterize these things. So whenever you have two quantities, you want to always see them as tuples. I mean, you want to see their collection, and you want to study the behavior of the collection of x and y, not individually x and individually y, right. So if you want to study those properties, then you have to define what is a joint moment, and so this is defined like this, which is nothing but expectation of x minus a whole to the power I, y minus b whole to the power j. This is a very generalized definition of a joint moment. But what we actually consider in practice is that we consider various types of things. We consider either, if we only want to consider that of x, then we consider what is known as variance, that is the old definition, x minus expectation of x whole square. Similarly, we can find out just the variance of y, which is expectation of y minus expectation of y whole square, old definition. But now we introduce a new quantity which characterizes that when x is lower than expectation of x, is y also lower than expectation of x, or is y higher than lower than expectation of y, or is y higher than expectation of y on an average. So we want to see them as tuples, we want to see their collective behavior. So is it that when this is positive, or is it on an average, and when this is negative on an average, or is it that sometimes this is positive, this is negative, this is negative, this is positive, all sorts of combinations occur. This is also a quantity of interest. Very often this is required to, I mean, especially to find out that whether the randomness of x and y are actually related. That is, if x goes high, x is a random variable, y is also a random variable, but is there a connection pattern or what is called a correlation in their variation patterns? Are they somehow related? So to be able to characterize that, we often consider this joint moment, which we call the covariance. So the covariance of x and y is defined as this into this. So obviously you can find out that if they are related, for example, if this is plus, whenever this is plus and this is minus, then the overall sum is going to be plus. So you have a positive correlation. On the other hand, if you have, it could be the other way. For example, you will also say that there is a correlation if whenever this goes plus, this goes minus, and wherever this goes plus, this goes minus. That is also a correlation. There is a pattern among them. In which case again the expectation value will be non-zero, it will be negative. But if in general this plus minus, plus plus and all the four cases occur uniformly, then you can roughly say that the variation pattern of x and y are really, they have no relationship. Sometimes this is positive, that is negative, this is positive, and these occur more or less uniform. Then this expectation value is going to be low. It is going to be a number which will be very close to 0. In such a case, x and y are said to be uncorrelated. Okay. So if whether there is a hidden relation between x and y is captured in terms of covariance. So we take covariance and we normalize it by the individual variation patterns of x and y, because we don't want to know that, we just want to know that is what is the degree of correlation between them, that is whether they move in the same way or they move independently and randomly, right. So these are very important quantities which are very often used, and we will use them in our future treatment in this course very often. So it's important to understand these I mean, first of all get familiarized with these concepts, and that then understand that what is it that I am trying to study, right. Now we will talk about certain inequalities or rather certain relationships, so which are also very often used. For example, we have these three inequalities which show some properties of which relate mean and variance, and they are used in analysis many times. So just wanted to introduce that. So for example, you have this Chebyshev inequality which says that probability that the magnitude or the absolute value of x minus Ex is greater than or equal to delta is less than or equal to the variance of x by delta square. So this is actually very simple to prove, because for any arbitrary random variable x, right. So how do you prove that? For example, what is the probability that, okay, let's first cover these things. So first of all, if f(x)x is equal to 0, this is there is another inequality which says that if you have only positive random variables, that is the random variable does not take values which are negative for all x less than 0, and so whenever x is negative, this is 0, which means that this random variable capital X takes only positive values. So if you have a random variable which takes only positive values, then the probability that this is greater than or equal to delta is less than expectation of x by delta, right. And finally we have covariance square xy is less than or equal to variance x by variance y, which means that the correlation value, that is the correlation coefficient that we have considered here, is always less than or equal to 1. That is what they are saying. So how does it happen? Let's start from the back. For example, expectation of x minus expectation of x into y minus expectation of y. This is covariance, right. So let us multiply, then we get expectation of xy minus y into expectation of x minus x into expectation of y plus expectation of x into expectation of y. If you take expectation now, you will get expectation of xy minus expectation of y, this will give you minus expectation of x into expectation of y. So this is your covariance xy. So if you make it whole square, what do we get? Now let us see the other end. So variance of x is expectation of x minus expectation of x, this into whole square into expectation of y minus expectation of y whole square. What is this? This is nothing but expectation of x square minus expectation of x whole square. Now you want to write, right. So this is this, and this is going to be multiplied by expectation of y square minus expectation of y whole square, correct. If you multiply them, what do you get? You get, so if you whole square this, what do you get? You get expectation of xy whole square minus 2 expectation of xy into expectation of x into expectation of y plus expectation of x expectation of y whole square. And here you get, if you multiply, first of all you get, if you multiply you will get this into this, right. So, this, so you will get expectation of x square into expectation of y square. Here you will get expectation of x whole square, expectation of y whole square. So, this term will get cancelled with this term, and always note that expectation of x square into expectation of y square is greater than or equal to expectation of x y whole square. This is obvious. Okay. So now using these properties you can very easily prove the prove this inequality. Similarly, by from simple integral formulae you can just try, and then we can consider this later on in a tutorial class, that you can very easily prove these properties also. There are other simple things. Today we are running out of time, so I will not get into proving this. So, I just wanted to say that there are certain convenient inequalities which are used and which are very simple to prove. So, I leave these as an exercise in the class which we will discuss in the tutorial class. All right. So, now what have we achieved today? So, today we have introduced the concept of a mean or an expected value, and we have calculated that for a number of cases, function of single variable, function of 2 variables, conditional expectation, etc. We have also found out that we have also introduced a measure of dispersion from the mean. So, we defined the variance in terms of as a special case of a general moment function, and we also defined the concept of covariance, which show what is the joint variation from this, and we finally defined the quantity of correlation, which is a very important quantity which detects whether two things are somehow related, whether they move up and down randomly, but whether their randomnesses are related. They are individually random, but they may not be fully random in their interrelationships. And thirdly, we saw 3 inequalities which are reasonably easy to prove, and we left it as an exercise. So, that is all for today. See you in the next class. Thank you very much.